Welcome to Voroshilov School. I'm Dr. Valentin Voroshilov, and this is Solving Problems with Dr. Voroshilov, a comprehensive guide to solving physics problems. An undergraduate physics student wants to measure the free fall acceleration. He drops a small nut from a roof of his barn, 5 meters from the nut to the ground when the student releases his fingers and letting the nut fall. Using his smartphone, he capturing the fall and then using frame-by-frame video finds that the nut reaches the ground 1.01 second after being released. What value does he get for G? Well, let's analyze the situation. As we know, some words are more important than others. For example, it doesn't matter that this guy is student or undergraduate. It doesn't matter if he is on the roof of his barn. What important is there is something above the ground and we let it go. So the situation is simple. This object travels some distance. It takes some time to travel this distance. We can assume something about its initial velocity. Well, of course, eventually it falls down with some final velocity. And the questions we need to ask are simple. What do we know? What do we assume, or what do we choose? What objects are involved? What do we know about those objects? What is happening to those objects? Or we can say, what phenomenon is happening? What processes are happening? What properties of those objects we know? What properties of those processes we know? These are the questions we should be asking again and again and again and again when we solve any problem in physics, or maybe in life. So we know the object is in free fall. How do we know that? Because it's released and it's happening close to the surface of the Earth. We know that its initial velocity is 0. How do we know? Well, we can read this word rest means the initial velocity is 0. Do we assume the initial velocity is 0? Well, no. We know the initial velocity is 0. Now, we also know that the height, the time, the acceleration is supposed to be related. How? Well, we could start thinking of equations, because the relationship in physics, every relationship in physics is represented by a certain equation. For example, I can write distance equals velocity times time. Can we use this equation? Well, we could assume that we could, and we could try to solve this problem and see if it makes sense. But this assumption probably wouldn't work, because for every equation there are specific situations when those equations work and then those equations don't work. This equation works only and only when there is no acceleration, or acceleration is 0. We know that when free fall is happening, something like this, the object is speeding up. Speeding up means velocity changes. And if velocity changes, that means acceleration is not 0. So we cannot use this equation. That would be a wrong assumption. Now we can go back to our picture. If velocity changes, how does it change? Well, again, we know that when any object falls down close to the surface of the Earth, it falls down with the same acceleration, which doesn't depend on the mass or shape of this object. Of course, we neglect the air friction, but neglecting air friction, the acceleration of this object has the magnitude equals to about 9.8 meters per second squared. Well, of course, in this problem, we should actually calculate this number and see if this student gets a pretty close result. But anyway, we know it should be speeding up. The acceleration should point down. And if we want to ask ourselves, what is related to what? And that's the most important question we should ask before starting writing any equations. We know initial velocity, final velocity, acceleration, time, those variables all related to each other. And of course, distance traveled also is related to these variables. How? That's the next question we should ask, and the answer is always provided by a specific equation. For example, here we can write, because the acceleration doesn't change, constant acceleration, the motion is happening with constant acceleration, initial velocity plus acceleration times time should give the final velocity. And we know that displacement, strictly speaking displacement, not distance, is related to initial velocity and acceleration and time traveled by the object by this equation. By writing these equations, technically we have finished analyzing the physical model, and we should be starting plugging in numbers and calculating whatever we need to calculate. But there is one more important point we should stress. Many physical quantities in physics are vectors. So for example, acceleration, velocity, displacement are vectors. And when we're writing an equation, any equation, we always should ask ourselves, in this equation, this variable, what does it represent? A magnitude or an absolute value, or a component? So for example, this letter A, what does it represent? Is it the magnitude of acceleration or its component? What is final velocity, this variable represent? The magnitude of the final velocity or the component of the final velocity relative to some axis? So using these equations means that we need to understand the vectorial nature of velocity, acceleration, and displacement as well. A, V, V, delta S, those variables represent components. And if we want to use components mathematically correctly, we need an axis. Well, usually we draw x-axis to the right and y-axis up or down, and it's up to us how we choose the direction. We could choose the y-axis straight up, or we could choose the y-axis straight down. Eventually, we would get exactly the same result for the magnitude of the acceleration we're looking for, but the mathematics would look slightly differently. So let's choose the axis. Well, in this situation, if you look at the picture, we can see two arrows pointing down. So if we choose the axis down, these components are going to be positive, and positive is easier to deal with than negative, so let's choose the y-axis straight down. Now we're supposed to choose the origin, the zero position, zero level. We could choose it here on the ground, or we could choose it at the initial position of the nut, or whatever object it is, doesn't matter. So now, relative to this choice, this component is supposed to be positive, this component will be positive. Well, in this problem we actually don't even need to use this equation. Initial velocity, as we know, is 0, and the only question is left is, what can we say about displacement? Well, if we measure the position of this object from 0 down, and it travels down by 5 meters, so 1, 2, 3, 4, 5. Here, y should be equal to 5, and the displacement, which is always final value minus initial value, should be equal to 5 minus 0, which is 5 meters. And now we don't need this equation. We can plug in numbers here. 5 equals 0 times time plus acceleration times, actually 1.01 squared divided by 2. This is of course a 0, doesn't matter if it's 1.01 or 1 billion. So the equation we need to solve is this. Well, whether we like it or not, but in physics when we solve a problem we're gonna do some math. In this situation it's a very simple math. This is our equation. So to solve this for our unknown, which is a, we just have to multiply everything by 2 at first, and then divide by 1.01 squared, and that finally gives us 9.8. Are we done? Well, not yet. In physics, most physical quantities have units, so we have to write the unit here. If we using metric system, meters and seconds, acceleration automatically has a unit, meter per second squared. And again, we said that in our original equation, A represents the y component relative to the positive y direction pointing down. But in this situation, the y component equals the magnitude of this vector. So the magnitude of this acceleration is also equal to 9.8 meters per second squared. We can ask what would happen if we have chosen the direction differently. A good question. The ground, the nut. Let's choose the direction, the positive y direction, straight up. So our acceleration points down. The equation we are using is this. The displacement equals the initial velocity times time plus acceleration times time squared divided by 2. We need to remember that when we're writing this variable a, it represents the component of the actual vector. Well, initial velocity is 0, that gives 0. So again, the question is, how do we calculate the displacement? Well, first we have to choose the 0, the origin. Let's do it here. That's the initial position. Final position is here now. It is 5 meters below 0. So if we go above 0, we read positive readings, 1, 2, 3, 4, 5. But if we go below 0, we should read negative readings. So -1, -2, -3, and eventually -5. And the displacement, as we said, always equals to this difference, final value minus initial value. So -5 minus 0, -5 meters. And now our equation looks slightly differently. If we solve this equation, the answer is now -9.8 meters per second squared. What does it mean? Well, again, as we said, this variable represents the component of this vector relative to this axis. If the result is negative, that means this vector has a component opposite to the direction of the y-axis. So if the y-axis points up, that means this acceleration actually points down as it should be. And the magnitude of this acceleration, that's what we call g, still equals 9.8 meters per second squared.